Welcome. We're going to walk through an actual Manual J report we have created as part of the resources provided by the Minnesota Energy Code Support Program. We will break down where to find the information, what the information is referring to, and what this information is actually demonstrating. You can follow along the information provided in the video by downloading the Manual J Breakdown Technical Document. To do this, you will need to go to the program's webpage at www.minnesotaenergycodesupport.org. Click on the Technical Document tab that's located at the top of the screen. Hover over the boxes until you find the one labeled as Breaking Down a Manual J. We will utilize this document to demonstrate what is listed in the report. Now that we have the document in front of us, let's look at the project summary page. It contains boxes outlined in red with a letter attached to these boxes. Each of these lettered boxes found in this report will have a correlating explanation of what this information is referring to, and you can find that throughout this document. Any software that is utilized must be ACCA approved software to be code compliant to perform a Manual J. Currently, these are RightSoft Right-J8, Elite HVAC, AdTech AccuLoads, Florida Solar Energy Center's Energy Gauge, CamelSoft HVAC ResLoads-J, Avanair MJ8 editions of HeatCAD and LoopCAD, CoolCalc Manual J, Conduit Tech, Amply Energy. A few of these softwares are actually web-based software as opposed to downloadable software. So this example has been created utilizing the RightSoft software. The project summary report is one of the many reports that RightSoft software produces. This report does not provide all the details needed for a heat gain and heat loss calculation. However, it does provide many of the details needed to make an accurate load calculation. So verifying this information that's shown in this report is a great place to start for jurisdictions, and it will have at least verified that the base design parameters are correct. Now, other software packages will have different types of reports and will include a lot of the same information, although it may be contained in several reports rather than consolidated into one report, as shown here with the RightSoft project summary report. Let's look at box A. This is the beginning of the design information that's needed for each project. So box A refers to weather. Now, this report shows St. Cloud as the location this project that is going to be built in, and the weather should list the location that this report is really being designed for. So the software may not contain every location within the country within its weather database. Now, if this happens to be the case, then you should pick a location that's near the location of where the project will be built. For example, if this report was for a project being built in Hermantown, Hermantown may not be listed within the database, but you could select Duluth as the location. Box B. Now, box B is the winter design conditions, and you'll notice there are 3 rows: outside dry bulb, inside dry bulb, and design temperature differential. Now, so that we can all be on the same page, dry bulb is the temperature of the air that is measured by a thermometer that's exposed to the air, but protected from moisture and radiation. So the first row is the outside dry bulb temperature that the software must use for the winter outside temperature. This information can be found in Table 1A of ACCA Manual J, or from the weather station for the area, or the jurisdiction may have adopted their own outside dry bulb temperatures. Now, this temperature is not the coldest it can be, but it's the 99% winter dry bulb, meaning that only 1% of the total hours for the year is it going to be colder than the temperature set in this row. The second row is the inside dry bulb. This is what the temperature is designing to for quote unquote comfort. This has been established through ACCA and through ASHRAE. The third row is the design temperature differential. This is where we add the outside dry bulb with the inside dry bulb. In this case, we are adding the negative 18 from 70, which gives us a difference of 87 degrees. When it is negative 17 degrees outside, it's making up 87 degrees of heat to be able to reach the 70 degrees inside. Box C. Box C is the summer design conditions. Now, this section contains 6 rows. The first row is for the outside dry bulb. In this report, it's listed as 86 degrees. Again, this is not the warmest it can be. This is the 1% summer dry bulb, meaning that 99% of the total hours for the year will be cooler. And you will notice that it's been bolded, and that's because the designer had to go into the software to change the design temperatures to what has been established by the jurisdiction, and it wasn't listed in the software. The second row is the inside dry bulb. Now, this is set to 75 degrees as suggested by ACCA designs. The third row is the design temperature differential, the difference between the outside dry bulb of 86 degrees and the indoor temperature of 75 degrees, which equates to 11 degrees. That is what this line is trying to demonstrate here. So row 4 is to determine the daily range for the temperatures. For places like St. Cloud, this would be listed as medium. This is determined by the degree swing as shown on the screen. So for medium, the difference is between 16 degrees and 25 degrees. Line 5 is for the relative humidity for indoors. For comfort, the design of the indoor relative humidity is 50%. Line 6 is showing the moisture difference, often referred to as the design grains. Now, this is the difference between the humidity ratio found in the outdoor air and the humidity ratio of the indoor air. In other words, what is the moisture in air on the outside compared to what the moisture is on the inside? So that would be 50% relative humidity. Now, for Minnesota, there will be a positive number in this line. If this was a dry climate like New Mexico, the number listed here would be a negative number. Let's take a look at box D. Now, box D is our heating summary. The first row is demonstrating the structure heat loss, and this is heat loss from the thermal envelope, such as heat loss from your ceiling, your walls, your windows. This is where your thermal envelope is going to have an impact. The second row is to indicate if there are any duct heat losses. There'll be a number in this row if the duct is located outside of the building's thermal envelope. If all the ductwork is located within the thermal envelope, there should be a 0 listed in this row as demonstrated in the report. Now, just as a note here, there could be a small number listed here if the ductwork happens to be located in an unvented attic or an unvented crawl space. Like I said, there might be a small number there. And just because it's technically located within that thermal envelope, these spaces are not typically conditioned like they are in our quote unquote living spaces. The third row is showing the heat loss from outside air. Now, this could be coming from ventilation air from outside that's being piped directly into the return air ductwork. from an HRV or ERV, combustion air, if there happens to be any that's being brought in through ductwork. Now, this report is demonstrating that there is 0 CFM being introduced into the return air system. So remember, the whole house mechanical ventilation system should be included in the calculation. The fourth row is showing any heat losses from installing a humidification system. This design does not include humidification systems, so the number is 0. The fifth row is heat losses from any piping systems. Now, this would be from like hydronic systems. And since this project is designed to a forced air system, there is no load here. The sixth row is labeled as equipment load. And when you add the previous rows together, it should equate to the number that's listed here. Now, the number listed in the report for this row is 35,164 BTUs an hour. This is the calculated heat loss. So this will be the minimum capacity of the heating appliance in order to heat the structure to 70 degrees and meet the designed temperature differential of 87 degrees. Box Z is the sensible cooling load. So sensible load is the heat gain of the home due to conduction, solar radiation, infiltration, appliances, people, and pets. For an example, burning a light bulb would add sensible load to the house. So the first row is showing the sensible heat gain of the structure. This is from the thermal envelope. So again, it's including things like your insulation values for your walls, ceilings, floors, slab edge, windows, the heat gain from people, equipment, and infiltration. Row 2 are the loads associated with the ductwork. If located outside the thermal envelope, they'll show a number there. If there's a 0, it means that it is located within the thermal envelope. Row 3 is showing the heat gains from outside air. This is similar to what we found in box D. Now that can come from the ventilation air from outside that's being piped directly into the return air ductwork, from an HRV, ERV, combustion air. All of these are going to add loads to this row. Now, this report states 0 CFM of unconditioned air will be introduced into the return air system. So row 4 is for the heat gain from the furnace blower. So this will typically have a very low number. If you get something that shows 2,500 BTUs or more, you'll need to ask for documentation from the manufacturer for the blower heat. The software defaults to 500 watts that results in 1,707 BTU H load, which equates to 1 watt equaling 3.4 BTU H. Row 5 is use manufacturer's data. Now, this should be selected to say yes. This is going to affect the rate swing multiplier in the following row. This is Wrightsoft's attempt as a manual S. Now, there is no ACA approved manual S software out there. So this needs to be located as yes. Now, row 6 is the rate swing multiplier. And if the previous line says yes, it's going to make this row show 1. If there is a number any other than number 1 that's listed here, you need to ignore the number in that next row, and you'll have to basically manually add the values that were listed above for structure, ducts, central vent, and blower, and that's the number that you would use. Now, if this number is 1 listed in this row, then you can use the number that you'll see in the next row. Row 7 is the total sensible heat gain. This is the number that is added to the latent load to determine the total cooling load. Box F. Now, box F is the latent cooling load. Now, latent load is the net amount of moisture added to the inside air by people, plants, cooking, infiltration, ventilation, and any other moisture source. So row 1 is the latent heat gain for the building thermal envelope. So this is again where your R value for insulation and the U factor in solar heat gain coefficient of glazing, along with other variables, will have an impact on the loads. Row 2 is for the ductwork. Now this report is showing 0 BTUs, meaning that the ductwork is located within the thermal envelope. Row 3 is for the central vent, very similar to what was found for the heating summary and the sensible cooling equipment load sizing boxes. The same 0 CFM applies here. Now, where it does differ in the moisture difference line that you'll find in box C in that last row, the number that's associated here can have a direct effect for the latent cooling load. That is why the moisture difference number is so important. If this was a dry climate like Clovis, New Mexico, this number would be a negative number and would not have a calculated latent load. But we're talking about Minnesota, and in Minnesota, there is going to be a latent load. So that is because the intent is that we are trying to dehumidify the air. The last row in this box is the total load. This is where the equipment sensible load from box E is added to the equipment latent load from the row above. In this example, we would add 14,405 BTUs to 2,363 BTUs to give us a total of 16,768 BTUs. The last row is listed as required total capacity at 0.85 sensible heat ratio, which is that SHR. The SHR is the sensible load divided by the total load. Now, for dry climates, it might be 0.95 to 1, but this is a moist climate, so we're looking at the 0.85. Now, this is the software's attempt to perform a manual S. And remember, like I said before, there is no ACCA-approved manual F software, so ignore this line. The correct number would be the 16,768. So what we will do is take that 16,768 and divide it by 12,000, and that is the correct tonnage of cooling required, which is the 1.3 tons. Let's look at box G. Now, box G is for the infiltration. How leaky is the house? Row 1 is showing that the designer is using the simplified method for determining the air infiltration rate. Row 2 is the construction quality. New homes will be semi-tight or tight. Now, designers at first may use average, which is acceptable, but it should not have anything listed, anything less than average for a new home. Now, calculations done for an older home where no blower door test was involved would utilize semi-loose or loose. The third row shows the number of fireplaces. Now, this is typically referring to wood-burning fireplaces because they tend to be leaky. Now, most gas fireplaces are tighter, and I wouldn't necessarily require that to be listed here. The next section is the box that is dealing with other parameters of the design for the structure. So that first column there is the category and what was used for the design. The area row shows the square footage of the actual conditioned area and not necessarily the entire house if it isn't all being conditioned. For example, if the house happens to be a total square footage of 2,000 square feet, but only 1,000 square feet of the house is going to be conditioned, then only 1,000 square feet would be listed in this row and not the 2,000. The next row is volume, and this would be the volume located above grade. The third row is the air changes per hour. Now, these are the values from the average construction type that's been listed above. And the reason this is different is that the heating is done with a 15-mile-per-hour wind and the cooling is done with a 7.5-mile-per-hour wind. The last row is the equivalent AVF or CFM, and this is the number of CFM that's coming through the walls. How leaky is it? These are the boxes of this report that are attributed to a manual J. Now, if you notice, we did not talk about box H or box I, and that's because these are associated with a manual S. So join us for our next video as we break down a manual S.